Yeah, I'm going to present to you guys what I did for my master thesis, essentially, which is called language control. The whole idea is how do we take robotics from last year and make it such that people and humans can talk to robots, interact with them in a very natural way. And the most natural mean is language. So thanks to the advancement of AI is how can we add AI to robotics today? Um, so what I'll talk about is quickly give a description of what robotics looks like today, what's the general pipeline, and then how can we actually go from natural language to control. And then if you guys have some questions, I will answer them. So this is pretty much how robotics looks today. It's looked like this for about, I don't know, 68 years. As you can see, there is really no human around. Robots today are not designed to interact with the human. As a matter of fact, usually have barriers to separate humans from robots. And they are single purpose. They do one thing. They do it very well. So I'm not claiming that should be changed, but they are designed with just one purpose. And if you want a robot in your home that's gonna, I don't know, peel an avocado and change a light bulb, probably these robots don't really work. And they have very much hard-coded functionality, which means you know exactly what they're going to do. They are robust to one disturbances, but that's it. They don't change plans. They do one thing, and that's it. So let's look at robotics today as a robotics pipeline. Let's say we have a robot manipulator like this, and we have a trajectory. Given a trajectory we want to follow, we have a controller, which is known as a PIT controller that helps us with that. So what does it do exactly? A PIT controller tries to track and follow a trajectory. In particular, it decides, given my current position, so the position of the gripper, for example, and given the trajectory that I want to follow, it decides how much torque to apply at each one of the joints of the robot to actually follow that trajectory. It's known as generally as a trajectory tracker, and it works at high frequency, meaning at 200 hertz. Every second, it applies a control input 200 times. But then the question is, how do we generate this trajectory? And for this, we have something called MPC planner. MPC stands for Model Predictive Control, and it's usually designed by the robotics engineer to generate a trajectory, to essentially tell the robot, okay, what you actually have to do. And while PID controllers usually come out of the box with a robot, so each robot generally comes with a PID controller, the MPC planner is something that the person has to design, or the roboticist or the programmer. I will quickly describe how MPC works because it's the core concept here, but it's not very difficult. So we are at the current time, and what MPC does is it generates a plan, meaning you get the measurements from all the sensors on the robot, and you have a model, a physical model that describes how the robot moves. So you generate a plan. What you do with this plan is you apply the first action in the plan or the first set of actions in the plan, and then you discard the plan completely. You measure newly from that point, and you generate a new plan from scratch. And you keep doing this. So you just take the first action of the plan, and you keep regenerating the plan. And this is known as receding horizon control, because every time you keep receding your horizon. Okay, and how do you actually generate this plan? Well, model predictive control, as I said, is an optimization problem. So you have to minimize some objective function. Here, your variables are x, which means the state of the robot. This may mean the position of the gripper, right? And u, which instead are the controls. So how much force to apply at the motors of my robot. Then you have constraints. For instance, the system model. The system model is generally derived from physics, and it describes how a robot will move if I apply some control u at time k, and I am at the current state. So if my robot is in a given position, and I apply this amount of torque, then at the next time step, I will expect it to be in this position xk plus 1. In addition, in MPC, you can define your constraints. You may say, okay, I don't want my robot to collide with other objects. So what you can input state constraints and say, okay, stay at this distance from that object that I want to avoid. And you can also do this for the control constraints. So you can say, okay, my motors can apply only maximum of 10 Newton of torque. So don't do more than that because it's going to break. And finally, you have what is called an initialization. And if you remember what I said before is you take a plan, you do the first action and then you reinitialize. Reinitializing essentially means, okay, I look at the measurements of the current state of my robot, and then I start replanning from there. And then the question is, okay, how can we take an instruction in natural language and give it to a robot? And there are a few methods here and a few philosophies. One of them is have a neural network that directly goes from language to the control, so to the force to apply at each joint of the motor. And another approach is to sort of layer it. I follow the second because it's easier, let's say. If you have a task like such, you have a robot manipulator, and then you have some cubes, and you want to ask it, okay, actually, I want you to stack the cubes. How can you actually achieve this task? And as I was describing before, this is the robotics pipeline today. And to go to the language instruction, we need a second piece here. And thanks to the advancements of Gen AI and GPT and OpenAI and etc., we can actually use an LLM, or in particular, a language model. So what happens here is you have the user that gives an instruction after observing the scene. The LLM sort of decodes that into the objective function and the constraint functions of the MPC planner. The MPC then gives the trajectory to the PID controller, who then decides how much torque to apply at the joints of the robot. So it's not enough to actually just have one LLM, because it's a very complex task. You have to understand what to do, and then you have to program an MPC controller, which usually is done by roboticists and people who have studied robotics. So I divide this piece into two parts, a task planner and an optimization designer. So the task planner gets the instruction and formulates a set of tasks. And for each task, the optimization designer converts that into the objective function and the constraints of your MPC controller. So what does it look like? If I say to my robot, okay, I want you to stack the cubes, what the task planner will do is, okay, create a set of tasks. For instance, go to the blue cube and avoid collisions. Then close the gripper. Then go on top of the red cube, etc., etc. For each one of these subtasks, you have the optimization designer who is going to decode that and formulate them into objective function or a cost function and constraints. Here, what you want to do is, what it's telling the robot to do is, I want to minimize the position of my gripper with respect to the position of the cube with an offset on the Z direction. So I want it to be D centimeters higher than the position of the cube. And the constraints is, I want the gripper to be at least D minimum distance from the red cube. And I want the gripper to be at a minimum distance from the green cube. And of course, I'm not going to ask GPT-4 to formulate it like that, but rather to write code for it. And there is a famous library for writing MPC problems, which is called Casadi. And you can just input that. You can tell GPT-4 to write the code for that. And that just becomes plug and play. Of course, you have to do some JSON formatting, and it's just plug and play into your MPC controller. I've done 6 experiments to show, okay, the potential of these methods. So for the first 3 experiments, it's just about playing around with cubes. So it's about asking it to stack cubes, to build a pyramid with them, or to write the letter L. And then for the other cubes, they're a bit more complicated. So you can ask the robot to clean the plate using a sponge, or to move a sponge to the sink, or 2 robots to cooperate to move a table. So let's actually look at what this looks like. So for this task, I'm asking the robot to clean the plate. What I'm telling it is, okay, there is a sponge on the table and there is a plate. What happens is the task planner is going to generate a set of tasks, move the gripper to the sponge, then close the gripper, and then move the sponge on top of the plate. And then it's going to define this, do a circular motion to clean the plate. And for each one of these subtasks, the optimization designer is designing an optimization problem. So an MPC formulation to actually clean the plate. As you can see, it starts cleaning the plate. It's a bit slow, so I can give it feedback. And I say, okay, actually, it's a bit slow, just go faster. And it's able to understand what is wrote before, and so increase the velocity, the required velocity of the gripper. Another task that I really enjoy is write the letter L. And the reason for this, it shows the power of using existing techniques like model predictive control. And what you can see here is that, okay, the robot is actually rotating each cube. And this is not described by the LLM. The LLM is just giving, okay, I want you to move the cube next to this cube and to avoid collisions. And based on that, the model predictive control, which, as I said, is an optimization problem, figures out what's the best configuration for the gripper to actually follow that plan. Here is a collaborative task where you have two robots, and what I tell them to do is, okay, you have to move the sponge to the sink, but I don't want you to drop any water because the sponge is wet. So figure out a way for the two robots to collaborate and achieve this task. And what they do is one robot takes a sponge and the other the pan, and as they move towards the sink, they make sure to be right the sponge right on top of the pan, such that if any water is dropped, actually it's dropped on the pan and not on the table. And this was the original way that I was thinking the robots to solve the problem, because I was thinking of carrying a sponge with my hand and then putting the other hand beneath it to actually move it to the sink. And sometimes I was actually surprised because there are more efficient ways, which I hadn't originally thought about. And it essentially consists of dropping the sponge on the pan and then moving the pan. And then finally, you have the task of moving the table behind the obstacle and avoiding collisions with the obstacle. And this task is fairly complex. And the reason is the number of constraints that you have to use here is quite high. The constraints that you need to achieve this is that, okay, both grippers have to take the handles of the table. And when they move, they have to remain at the same distance. And the reason is you cannot really bend the table. So if you push too much or pull too much from each other, either the robots break or the table just falls down. So you have to use these constraints. And this is the power of model predictive control, because you can define constraints, and it's something that you cannot really do with learning techniques. And also avoiding collisions is something that you can directly give in your formulation. So I want the position of my robots to be bigger than some minimum distance compared to the obstacle. This is pretty much it. So this is more work that I think is really interesting, and it goes into the direction of, okay, how to use the newly rising LLMs with robotics and with agents in general, and also blog posts are both. So I'll share the slides on Discord later. And yeah, feel free to shoot me some questions.
This is super cool. I got a few questions.
Yeah.
So when you talk about constraints, can the task planner come up with those constraints, or does the user have to like kind of bake that in before they request an action?
So it's generally the way you have to prompt the task planner to actually give constraints. So that task planner can give constraints. And what happens here is when it says, go to the blue cube and avoid collisions. So this is generated by the task planner. And then this task is taken by the optimization designer and it formulates this constraint. So if you prompt properly the task planner, you can have constraints baked in.
Okay, and I'm assuming that GPT-4 knows the inner working of the MPC library that you mentioned.
Exactly.
So the task planner can give it to the optimizer, and the optimizer would actually write Python code based on that library.
Yeah, that's correct. So the library is called Casadi. It's like fairly standard, but you can use there are many libraries. What I assume happened was that this is in general optimization code. It's not really like specific to MPC. So I believe like it's like pre-training data set has seen a lot of that code. So it's pretty good at doing that.
Yeah. So what is optimization code? I think that's something that I haven't heard before.
Okay. Are you familiar with something called CVXPy?
No. I'm like
okay.
I'm like a full stack web dev person, so this is pretty new to me. Yeah.
Okay. Let's say so PyTorch. What PyTorch does is optimization, right? And the way that happens is gradient descent. Let me see. I have the code. I have this here. Okay. So an optimization problem essentially is, okay, I have some variables. I have to make a decision. So these, in my case, are X and U. When you're training a neural net, what you're deciding on is the weights of your neural net. And then so there are three components: decision variables. So what am I allowed to choose? What do I have to choose? And then you have a objective function, which is also called the reward function. It's a metric that defines how well I'm doing it. And then you have constraints. And the constraints define, okay, I have some limits that I cannot go over. The whole idea here is when you're training a neural net, for example, on a classification task, there's your reward function is saying, okay, I want you to guess correctly if this is the image of a dog or a cat. And it's the same here. And what it updates, what it decides are the weights of the neural net. And and then you may have some constraints. The difference between, I don't know, PyTorch code and this sort of optimization is that PyTorch generally solves this problem using gradient descent. So you have your batches, you train, you see how well it does, and you keep changing the weights based on gradient. So you follow the gradient. In model predictive controls, something similar happens, but it's not data-based. So I have my own functions, and I'm optimizing over these functions, which are mathematical equations. So I don't really need to collect data. What I have this function L, which basically says, if you remember, I was saying it's a receding horizon. So it goes from the beginning, so my current time, up to this time. So this is my horizon. And my objective function is over this horizon. And I can show you here. Here your, let's say, objective is X of the gripper is the position of the gripper of the robot. And X of blue cube is the position of the cube. And then you can ignore this offset. So I want to minimize the norm. This is the norm. So meaning how far the position of the gripper is to the position of the cube.
Gotcha.
And this is
okay.
And this is what you want to minimize over your horizon. And
So it's
then
trying to find its path to the blue cube, red cube, whatever, right? And then you almost, when you say reward function, that kind of like clicks for me, because it's like this kind of follows the same pattern as like training for a reward function, like a what do you call it, like a PO or something, or P0?
PPO.
Yeah, PPO. Yeah.
So the difference is it's just about like the sign. So when you have a reward function, you want to maximize your reward. When you have a cost function, you want to minimize your cost. And generally, what happens, you can just put the negative sign, and it just flips. So your cost becomes your reward, and your reward becomes your cost.
Gotcha. So do you want to go back to the slide where you have like the receding, whatever that's called? So are you saying that from the time that the robot starts to the time of the robot being able to grab the object, you have to call an LLM like a dozen times for it to like optimize itself to get there?
So this is a good question, in the sense that no, you don't. You don't call the LLM a dozen times. You call the model predictive controller a dozen times. So you modify your model predictive controller a dozen times. So there is a series of loops in there. And so it's like
programmatic. It's not like LLM rewriting the Python code for the MPC part, right?
So you rewrite the Python code only for each one of these tasks.
Okay.
So so this is the task. Okay, go to the blue cube, avoiding collisions. It's gonna formulate this code. It's gonna apply this code. Once this is done, it's gonna go to the second task. So close the gripper, and this is straightforward. And then the other task is go on top of the red cube, and it's gonna formulate a new MPC formulation, right? And it's gonna apply this until it goes on top of the red cube, and then it goes back and opens the gripper.
Gotcha.
So you generate the task, the whole plan once, and then what you do is for each one of these tasks, you call the optimization designer once for each one of those.
Gotcha. One last question, and then I'll open up the floor for everybody else. So for the two arms example, do they both share the same task planner, or how does it work?
Yeah, they share the same task planner. That's generally easier. There is some work where each one of them has a separate task planner, which is called Roco, and they literally chat with each other before deciding what to do. So my way is okay. One is deciding for both, and here you have two LLMs chatting with each other and deciding what to do.
Imagine like the Tesla Optimus, or like those like humanoid robots walking around. Like, it's literally the same concept, right? Like you give it a command in natural language, or probably like use GPT or whatever, a transformer model, turn that into a task planner. Task planner goes into optimization function writers, hook up to like an MPC kind of like library, and then translate that into a trajectory that the robot can go to or achieve. So this
Yeah.
has been pretty great. This really blew my mind how like straightforward it is. So
Yeah, it's pretty simple. Yeah, I was surprised it was this simple to do, but yeah, pretty cool.
awesome. And have
Okay.
you tried this in the real world yet, or?
No, I haven't. We didn't have the time. Yeah.
Cool. Anybody else have any questions? Rami, I know you just joined, but feel free to ask anything.
Thanks, guys. I just joined, but Seif, I've been kind of reading your blog and checking out your GitHub. Super impressive stuff. I'm really kind of curious to learn more. Sorry, I was a little bit late. I had a doctor's appointment that I just came back from. But yeah.
I don't know. Maybe I can. Did you see the video examples?
No, I saw that video on their post. Yeah, exactly. I've already seen this one. It's pretty cool.
Okay. So
We're
let me
gonna
show
get
you.
you real robots to test with now.
I mean, yeah, that would be amazing. I think so. Today, Stanford just released a paper that like works super well. Of like it's a very cheap setup of two robot manipulators, and it works pretty well. And like, I mean, that would be amazing to test on that. Yeah, that would be really cool. I think, yeah, a lot of people are like really working in the software world, and I think there is a lot of potential with robotics, but it's just going to take so much more time and so much more money, especially. But like the potential is there. I mean, part of the reason why I wanted to present was okay to like get people hyped about robotics as well. But yeah,
I'm
like
definitely super hyped.
I am super hyped. I think it gets you super hyped. But yeah, maybe we can work together one day.
Yeah,
But
absolutely. I remember Rethink Robotics when they first launched Baxter Robot. I don't know if you remember that one. It was like in 2012.
yeah,
Super cool technology, but one of the biggest challenges was how long it took to program it to do tasks. That was a big complaint because it was like 35K to get it deployed, but then
yeah.
have to spend like hours reprogramming it every time. So now imagine you can just have a conversation with it every time the task changes at the factory floor or a distribution center, and becomes much more compelling, right?
Yeah.
So
I think like so it's a bit I've been super interested in this field, and I also wanted to start a startup on this, and I've been looking around a little bit, and what I think the best way to go about it is not really to like think of like existing industries and going there and say, hey, look guys, this is what I made, like maybe you try to adapt it. Like they are like pretty much dinosaurs, they don't really want to try this. So I have the sort of inkling that even if you could talk to it, they wouldn't be super convinced. So generally my approach would be like to start a competing business against them using robotics and show that it actually just works so much better, and you just build it around that. And I think that like this would be so valuable, but it's like also so hard. But yeah, definitely, yeah. Like now it's a lot easier to do, and with vision. So here, like one pitfall that I see is that okay, you don't really have vision. So you have some perception that describes the scene and gives the observation to the LLM, but it's not specifically looking at that. So this was before GPT-4V came out, but right now it's time you can really put that in, and it can just do everything completely by itself, and then try on real robot. Yeah, that would be amazing.
yeah, I think the multimodal aspect is really what's going to make it, really pop in 2024. And either way, it's kind of cool to see a lot of the new. My hunch is in this year we're going to see a lot more on the multimodal side, which is only going to make this use case much more likely. And the nice thing about robots is a lot of robotics companies now are starting, like the hardware is getting commoditized, right? So you think about most of them are starting to rely on ROS, robot operating system. So it's open source standards. You can, I don't feel like you need to deal with those dinosaurs as much anymore. Like there's just enough solutions out there that would let you build software on top and make things happen. So it's very cool. Yeah.
I have my
What's
thought.
that? What's ROS?
Yeah, so ROS is essentially this entire system that people build robot software on. It's called robot operating system, but it's not really an operating system. It's more of like a middleware. Essentially, the key feature that it does is all this communication that happens between different components, it takes care of it. So it's very much of like a publisher subscriber type of programming. So my MPC planner is going to publish the trajectory somewhere, on the system, and then the PID controller is going to read it from there. So it allows you to code in very modular ways, and they have a lot of things baked in specifically for robots. And one of these things is called raw specs. And so inter-messaging and raw specs are, I think, the two key things about ROS. And raw specs are essentially you log everything, and you save it in a format such that you can replay, it, like with time adjusted replaying of what happened. And this means that you can replay a scenario, you can go back, and it's synchronized. And these are the two key features about ROS. The reason why you've probably never heard of it is because it's so damn hard to actually install and use, at least at the beginning. So it just works with Ubuntu if you want to use it. And then trust me, it takes about 1 week probably to install it. So I think—
Is it 1 week?
Yeah, I mean, if you're a newcomer,
Whoa.
yeah. Because like
Somebody has to write like something like that, but in like Python, that takes like one pip install and it's up and going. I can try it.
Exactly. So what I'm hoping for is for a startup to come out and say, "Hey guys, I've rewritten ROS." So the reason why it is like that is because robotics people are very mixed. So it's not just software developers; it's like mechanical engineers, all these things. And generally, when you deploy your robot, the computer on the robot is Linux, so it's Ubuntu, and you don't really have this problem of I have users that are using macOS and users that are using Windows. So that's why it has remained like that. But I feel now there is the incentive to actually switch. So I hope for somebody to one day rewrite it and make it much easier to use.
Dude,
yeah.
I don't know about you guys, but I already have so many ideas in my head. Because like we can all kind of feel this is where the world's going, right? Like all these big incumbents are coming out with like robotic, like reimagination of like humanoid hardwares and stuff like that, right? So that's where the world's going. But like you said, the software is pretty archaic. So
Yeah.
somebody has to step up and fix that, right? So
robotic software is super archaic. It's crazy. So I presume, so I know that companies generally have their own software. So NVIDIA does their own thing. They don't use ROS. They fork it and then they change it. And I suppose Tesla does the same thing. Yeah, so ROS is the type of thing that you build and it's like open source software. So I don't think there is a lot of money there, or at least you have to figure out a different way to actually capitalize on it. But it would be so much valuable. Yeah.
Yeah, agreed. There is some cool companies. There's one in Montreal called Ventian that's worth paying attention to.
Okay.
They're trying to make the deployment of robots so much easier, right? By you basically like describe the task, you can literally order everything, and like as a factory floor or warehouse, you could just assemble it pretty much yourself. So imagine now like that plus this software, and you could technically automate a warehouse or factory floor or part of your manufacturing in like weeks instead of years usually, right?
Yeah. Yeah, I'm really excited about robots in the house as well. I feel if we solve that, we're gonna solve everything else. But yeah.
I can't wait. I do think with like aging, but in looking earlier this year, I looked a lot at age tech. Like the forecast is we're going to have this massive number of people retire in the next decade, right? And the problem is we don't have enough people to support them, and a lot of them want to live at home. So how do you automate portions of the tasks? I just worry that like human psychology is not there yet to accept it. Yeah, who wouldn't love like a robot that can do their laundry or or the dishes or something? It would be a dream. Yeah.
I don't know. It's been very like romanticized for a lot of time, but like we were never able to nail it. And I think, yeah, I mean, AI is probably gonna solve that. And so all my techniques here are like they're model based. It's like the old way of doing things. MPC exists since the 1980s, so it's nothing new. But yeah, I feel like probably like the best way to go about it, if I had to go about it and actually bring it into the real world, it would be like just one neural net that does pretty much everything, which is what is starting to happen now. So yeah, I think it's gonna work.
are you saying that one day it's gonna be a neural net or like a large model that just kind of like become the base for any kind of robot that you want to put it in, and then if you can fine tune it to do certain tasks more certain ways better, then you can do that as well?
Yeah, exactly. I think it's gonna be a neural net that's gonna take care of everything. I mean, of course, you'll have to write some code that does some stuff just because it works for small things. It works a lot better. But overall, it will be like this big neural net that's gonna figure out what to do, and it's gonna do it pretty well. And then the problem that you really have with robotics is data. So LLMs work so well because you have this huge amount of data on the internet. And then unfortunately, you don't really have internet for robots, even though it's a concept that was proposed in 2012. Until we'll be able to collect a shitload amount of data for robotics, we're not going to be able to train these neural nets. But now things like the transformer make it such that the incentive is huge because it would work. So it's going to be time that we start collecting as much data as possible in the physical world. And until then, we won't be able to do it. But yeah, we're doing it right now. So yeah.
Amazing. Anybody else has any more questions? If not, any last words before we wrap up the webinar?
I mean, yeah, thank you for having me. I think it's a really cool concept. Yeah, and I'm looking to see what others will present.
Thanks for speaking, Seif. This was really cool. Looking forward to staying in touch too.
Yeah, definitely.
Yeah, and feel free to drop some resources in the Discord as well. Feel free to hang out, ask questions, or share things. We'd love to chat more about this in the future. I'm sure this topic is going to come up at some point, and maybe we'll even do like a hackathon for like LLM/robotics at some point.
Okay.
Maybe
I'll fly to Canada.
Judge.
Yeah.
Fly here, and we'll treat you like king. Like all you have to do is get here, and then you already know like 250 people. So
awesome, amazing. Yeah, thank you.
Yeah, man. That's it for the webinar. Thank you for hopping on, and
wish you a great
stay
one.
in touch.
Yeah, cheers. Have a good one. Bye bye.
Bye.